second talk is by Todd, Ambridge. It's about formalizing the Escardó-Simpson interval object in univalent type theory.
Okay, thanks for the introduction. So yeah, I'm going to talk about formalizing the Escardó-Simpson interval object in univalent type theory, specifically using AGDA. So I'm going to provide a motivation for this axiomatization of real numbers, show how this structure can be defined in the type theory, and show how operations and properties can be derived from the axioms. Finally, I'll show how a structure identity principle can be applied to interval objects. The classical specification of real numbers is as the unique, complete Archimedean field. In this talk, we instead explore the Escardó-Simpson axiomatization of interval objects based on a structure called a midpoint algebra. One of the key motivations behind this axiomatization is that it is exceedingly simple and also very generalized. A good example of this simplicity is that the multiplication function is derived from the axioms rather than an axiom itself. And the same goes for the property that multiplication is associative, for instance. The completeness axiom in the classical setting is replaced by an iteration property. A closed interval is then specified by a universal property that gives a computation principle for real numbers. And from this, we derive many expected operations and properties. So a quick glance at the previous work. Firstly, Martin and Alex proposed interval objects categorically in 2001 and showed that in set and top, the interval objects coincide with expected notions of real intervals. Steve Vickers continued in this fashion in terms of locales, and recently in his thesis, Alka proved that the Escardó-Simpson reals coincide with the HoTT reals, which was already postulated in the HoTT itself. So a key feature of this axiomatization is that it is specifically designed to support constructive mathematics. This makes it attractive for computability, and hence want to cast it to a HoTT setting is clear. As Carlo told us on Sunday, type theory is a kind of sorcery that makes maths work well on computers. I think a shared long-term goal is to apply this sort of sorcery to the real numbers. Conceptually, interval objects are initially intended to represent any closed and bounded convex subset of the real line. The word convex here means that the subset contains every point on the line between its endpoints. In order to define convexity type theoretically, we use the idea of taking the midpoint between two numbers, and furthermore that taking such a midpoint can be infinitely iterated. So an interval object begins with the structure called a midpoint algebra. This is a type equipped with a binary operation called the midpoint operator, and the type is required to be a set. A midpoint algebra is therefore a magma whose operations satisfy three properties. First, the midpoint operator must be idempotent. A midpoint A is just A. So second, it must be commutative. A midpoint B is always the same as B midpoint A. And third, it must be transpositional, which means that the midpoint of these two midpoints here, A midpoint B, midpoint C, midpoint D, can be arrived to in another way, which is A midpoint C, midpoint B, midpoint D. So this is a midpoint algebra. And we add one more property, cancellation, which says the situation where A midpoint C is the same as B midpoint C can only arise if A and B are identical. So this is now a cancellative midpoint algebra. Euclidean space is a cancellative midpoint algebra, closed under the expected midpoint function, i.e. take the two numbers, add them together, divide by 2. The rational numbers also form a cancellative midpoint algebra, as do various other subsets of the reals. So using this structure with two initial elements, 0 and 1, we could construct any dyadic rational number in the interval 0, 1. And these are exactly the reals with finite binary expansions. So a half is 0 midpoint 1, and we arrive at a quarter or 3/4 by taking another midpoint, and so on and so forth. However, we clearly cannot generate all points on the convex line. For example, using this procedure, 1/3 would require an infinite binary expansion. Thus, we require our version of the completeness axiom. The completeness axiom makes formal the idea that a line segment is convex, it has no gaps. But currently we can have gaps all over the place, everywhere there is a non-dyadic rational or irrational number. We require the ability to take an infinitely iterated midpoint, meaning that, given a sequence of elements of type A, we can take the infinite midpoint, 0, midpoint 1, midpoint 2, etc., etc., etc. And this operation is right associative here, so the earlier elements sort of have more weight on the infinite midpoint, if that makes sense. So the ability to take such an infinite midpoint is an additional axiom which says that given any sequence of elements, m of that sequence is the same as the first element, midpoint m of the tail of that sequence. And then there's a second subproperty for the iteration principle as well, which gives a sort of characterization rule of this m operator. And it says that given two sequences, if every item in the first sequence agrees with the midpoint of the corresponding item in the second sequence and the next item in the first sequence, then the first item in the first sequence is identical to m of the entire second sequence. And using these two subproperties, we can prove that m has some nice properties itself. For example, m of an infinite sequence of the same element should be the same element. And it's also a midpoint homomorphism relative to the midpoint operator. So a cancellative midpoint algebra whose operation is iterative, which means it has some such m operator, and with two endpoints in the underlying set, is called a bipointed convex body. That word convex again signals that we can now construct all points in the closed and bounded convex subset between the endpoints. For example, 1/3, our example from before, is constructed in 0, 1 using the m operator like so. So we finally arrive at the structure of an interval object, which is characterized by a universal property on bipointed convex bodies. The convex body with underlying type A is an interval object relative to a universe V, if given any other convex body in that universe with underlying type B, there exists a unique map H from A to B that preserves the endpoints and is a midpoint homomorphism. The universal property then says that a convex body is an interval object if it's an interval object relative to any given universe. It might be a little hard to wrap around what this map is supposed to be doing. So if we look at it visually, the idea is that if we have an interval object in blue here and another convex body in the universe V in orange here, then the map should preserve the endpoints and be a midpoint homomorphism. Therefore, this is a sort of affine mapping of points in A to the relative points in B. And furthermore, this map is unique, as I already said. And we can, of course, utilize the universal property on subintervals of A itself, giving us a map from A to A, which maps points in the whole interval to the subinterval. And because we can do this for any subinterval with endpoints A, B, we can add the choice of these endpoints into the map itself. What we now have for any interval object with endpoints U, V is a function aptly named affine, which takes two endpoints A, B, and then a third point that it maps to the relative point in the subinterval with these endpoints. And this has four properties. On the left, it has affine ABU equals A. On the right, it has affine ABV equals B. And then for any AB, it's a midpoint homomorphism and it's unique. So I'm just going to take us over to the actor now. Okay, so now let's take a look at what this looks like in Agda. As you can see, we have our function affine and our defining equations here. So we've got the left equation as before, affine ABU equals A, the right equation, the fact that it's a midpoint homomorphism for any AB, and the fact that it's unique. And it's just the type signatures here, because remember, these are axioms. And we then have the trivial corollary that any function f that satisfies the three properties, the left, the right, and the midpoint homomorphism, is identical to affine AB for any AB. This is identical point-wise, sorry. So we're going to fix our interval object for representing the interval -1, 1. So we rename our endpoints to make this clear, and we can then give 0 as the midpoint of the two endpoints. And now we're going to look at how operations and properties are derived in this setting quite nicely out of the current axioms that we have. So first, we want to define negation. And this is just given by the affine map that flips the interval. So something in -1, 1 is taken to something in +1, -1. So negation is affine +1, -1. And we get these three facts out of it. We get the midpoint homomorphism. So minus A midpoint B is the same as minus A midpoint minus B. And we get the two inverses. The inverse of -1 is +1, and the inverse of +1 is -1. So these come from the definition of affine here. And so we can convince ourselves that this is indeed the negation operation on -1, 1. And then we can show some fun facts. For example, -0 is 0 is quite easy. First, we use the fact that it's a midpoint homomorphism to transform this into -1 midpoint minus +1. And then we use the inverse facts twice to get 1 midpoint -1. And then because it's commutative, we can swap it over, and that's how 0 was defined up here. So to have sort of ultimate confidence in our negation function, we want to show that it's an involution, i.e. for any x, minus x equals x. And this is done by showing that performing double negation is the same as performing affine -1 +1, and therefore it's the same function because affine is unique. And then showing that this is the same as the identity function. And both parts of this just use the uniqueness of affine -1 +1. So first, we have to show that the double negation function satisfies the same left, right, and midpoint homomorphism properties as affine -1 +1. And this is quite easy. So on the left, we have to show that -1 is -1, and that's just an application of the two inverses. Then we have to show that -1 is +1, and that's the same, but swapped over. And then we have to show that this double negation is a midpoint homomorphism, and that's easy because we're just composing negation, which is already a midpoint homomorphism. And then showing the second step, that this is equivalent to the identity function, is again just from the uniqueness of affine -1 +1, but slightly simpler than up here. So negation can be easily defined, and we easily derive involution. I really want to convince you this axiomatization is nice and quite neat, so we'll also look at multiplication. Multiplication by x is defined as affine minus x. So x times y is affine minus x y. So if y is -1, it's taken to -x. If y is +1, it's taken to x. And if it's neither, then it's taken somewhere in between. And so we get these equations out here. For example, the fact that multiplication is a midpoint homomorphism, we have for any x, y, z, x times y midpoint z is the same as x times y midpoint x times z. So then we want to prove that this is associative. And again, this is just from a uniqueness of affine. So what we want to show is that these two functions here are equivalent. This one here on the left is clearly given by affine, lambda z x times y times z, because it's the affine map of negative this to plus this, as we see here, negative this to plus this. And then we simply have to show that this function here satisfies the same left, right, and midpoint homomorphism properties. And that it is a midpoint homomorphism, sorry. So on the left, we have to show that x times y times -1 is the same as minus x times y. And this is done by, first we apply the fact that y times -1 is -y. Then we use the fact that negation is an involution, which we showed a minute ago. And then we do this swapping lemma here, which is just another proof, separate proof. But again, it's relatively short and just done by the uniqueness of affine. And then we arrive at minus x times y. And then on the right, it's thankfully a lot simpler. It's just the fact that y times 1 is y. And then showing that it's a midpoint homomorphism is easy. It's just an application of the fact that multiplication is a midpoint homomorphism twice. So hopefully that quick look at the axiomatization convinces you that the axiomatization is simple, constructively appealing, and has concise proofs of properties that are usually axiomatized. So finally, I'm going to give a very quick run through of how we apply a structure identity principle to interval objects. So the structure identity principle is an informal principle that expresses that isomorphic structures are identical. The univalence axiom expresses this principle for general types with no additional structure. And we utilize the structure identity principle by Martin Escardó, formalized in the same Agda library that I'm writing this work, and that's already been introduced to us in Max's talk on Sunday. In this setting, equality is characterized by a general theorem for a standard notion of structure. We define an SNS for interval objects relative to a given type universe by the general theorem, a characterization of equality for such interval objects is immediately derived. So an SNS consists of a structure specification, which takes a type and gives back a type defining the structure. Terms of a structure are then given by terms of the type sigma S, i.e. a type equipped with that structure specification. We then have three other things, iota, rho, and theta. The iota is the definition of homomorphisms, or structural equivalences, if you like, on terms of the structure with equivalent underlying types. The rho is a proof that equal terms of the structure, AS here, satisfy iota. And the theta is a proof that, given a type A and two terms of SA, the map S equals T to iota AS AT is an equivalence. So, for example, the SNS for infinity magmas, the structure specification is just a binary operation on the type A, on the underlying type. The iota just says that the equivalence between the types is also a magma homomorphism. And the rho is trivial. And I've left out the theta here, but it's equally easy to construct, I would say. And now, given any SNS, we get the type of structural equivalences for sigma S using the iota. Two elements of the structure are equivalent if there is an equivalence map that satisfies iota on these elements. And the general theorem stated here can then be applied for any SNS to say that for any two elements A, B of the structure, sigma S, the type of structural equivalences, this type here, is equivalent to the identity type. So that is the characterization of equality that we get in this structure identity principle. So then to apply this to interval objects, an SNS can be defined for interval objects relative to a given universe V. So the specification says that there is a bipointed convex body that is an interval object in that universe V. Then the iota says that the equivalence map between A and B is a midpoint homomorphism, just like the magma homomorphism we saw with magmas, and also it has to satisfy the two endpoints as well, just as we saw before in the universal property. And then the rho again is quite trivial, and the theta is constructed by proving that satisfying the axioms of being an interval object is a property, which we've done in Agda if you want to have a look at the formalization. So immediately from applying the general theorem here, we get a type of equivalences for these interval objects. And from the general theorem, we characterize equality on these interval objects like so. The type of equivalences between interval objects is equivalent to the type of identities on interval objects relative to a given universe. So any two interval objects in a given universe U, and also relative to U, are equivalent by this above definition, and thus, by the above characterization of equality, are equal. What this means is that any two interval objects that can act on each other are identical. And this is sort of the final result of that structure identity principle application that's in Agda if you want to take a look at it. I've put my website address here. So to conclude, I've got 1 minute left, so I'll wrap up the talk. We formalize the Escardó-Simpson interval object in univalent type theory using Agda. Interval objects are defined using midpoint algebras and a computation rule for real numbers. And many expected functions and properties are derived from the axioms in a clear and concise way. And finally, a structure identity principle has been applied to characterize equality on interval objects. So I've linked to my website here, which has links to the 2 Agda files that are currently there for this work. And one of them is still ongoing, but it features some work in progress that's not shown here. So for example, on defining power series with the M operator, and then also adding an additional axiom called double. And this allows for the, this was in Martin and Alex's original work, and this allows for the definition of functions such as truncated addition and subtraction, the maximum, minimum. And we're currently working on proving that the nice properties fall out of this axiom as well. So, so yeah, that's me wrapped up. So if you've got any questions, I'll try and answer them. Thank you very much.
Thanks a lot. So, are there any? Yes. So someone is raising his hand. Mark Bickford.
It's me. So yeah, here's my question. What's the definition of two numbers in this midpoint algebra being separated? In other words, what's the definition of strict less than?
Well, actually, I'm currently working on that.
Okay.
So I can't give you an answer right now, but maybe in a couple of weeks I'll be able to.
Okay.
Yeah, email me in a couple of weeks.
Are there any other questions? So I have a very, very ignorant question.
Mm-hmm.
But there's a lot of noise. I don't know why.
Mm.
So yes. So the question is, yes, this is much better. Your intervals, are they finite, or is the entire real line an interval?
Well, they're bounded intervals, so we can't represent the entire real line, but we can. Well, I don't know if you can do the extended real line, but they have to have two endpoints, so they are they're bounded intervals, yeah. But we do get every point along that convex line, so if they're not necessarily finite, they're not finite because we can represent any point in this line using the M operator, taking the infinite midpoint. Does that answer your question?
Yes, somehow. But so how much of constructive analysis can you do without having the full real?
Well, yeah, I'm not sure really. I mean, I think Martin and Alex have looked at ways in which this can be applied. And then I'm looking now at applying it to some other work that I'm doing in constructive analysis and seeing what we can get out of that. But using the raw axioms as is, I've shown a lot of what we've got, and then we can get these maximum minimum functions. And then it would be nice to see how limits are defined in the original work. So we can define limits. So I'm wanting to do that in Agda as well. So there's a lot of analysis that you can do with this, but it would be nice to see if it can go further than what's currently there or in the original work of this, and see how much we can get formalized in Agda. So that's probably not the best answer to that question, but that's probably the best answer I can give at the moment.
Okay, thanks.
Okay. Thank you.
So I don't know,
Shall I stop sharing my screen?
Yes, maybe. And let's give a chance to anyone to raise his hand. Okay, so let's call it the end of your talk, and thanks again.
Thanks everyone, thank you.
So we have a few